Hello and welcome you all to Phonetic Engineering. In this video, I will explain projectile motion. Projectile motion is a form of motion experienced by an object or particle that is projected near the Earth's surface and moves along a curved path under the action of gravity only. In projectile motion, an object will have a velocity, its initial velocity and its final velocity here. In this picture we have a point A and a point B. Point A is the initial point from which the object is projected or launched, and point B is the final position. This motion will have two components. One is in the x direction and the other is y direction or in y component. As you can see, this object is projected at an angle of 45 degrees and we have a range, and range is from point A to point B. It is in the x component, and the distance from point A to point B, or from initial point to the final point, that is range. The only force of significance that acts on the object is gravity, which acts downward. The force will be applied, the gravitational force will act on the object which is launched, and it will be downward, and we will take that as negative. Because of the object's inertia, no external horizontal force is needed to maintain the horizontal velocity component of the object. In the horizontal component, or in x direction, there will be no extra force required because the velocity will remain the same throughout the component. Here no acceleration will be acting on the object in x component, and the acceleration along x component will be 0. Taking other forces into account, such as friction from aerodynamic drag or internal propulsion, such as in a rocket, requires additional analysis. In projectile motion, we use mainly the gravitational force acting on the object, while the air resistance, the aerodynamic drag and internal propulsion, these forces are neglected. If you want to add these forces or calculate these forces, so it will require additional analysis for finding the height, the range, or the other elements of the object in a projectile motion. The free flight motion of a projectile is often studied in terms of its rectangular component. The projectile motion is mainly taken in rectangular component, which are having the x component and the y component. Here you can see an object is projected in with a velocity v and having an angle of 45 degree. It is and this is the point A, the initial point. This will be the final point, or point B. So if we take velocity in x component, we will have its component in x direction, and the velocity will have two components. The one is in x component, the other is in y component. So further later on we will discuss how to take that components and how to use that components in the equations. To illustrate the kinematic analysis, consider projectile launched at point x0, y0. X0, y0 is basically the initial point, and this is the x0, and y0 or point A, with an initial velocity of v0, having component v0 of x and v0 of y. As I said that the velocity will have two components, the v0 x and v0 y. So v naught, if this is the velocity, so it will have v naught x in this direction and v naught y will be in this direction. So v naught y will be this component and v naught x will be this component. When air resistance is neglected, the only force acting on the projectile is its weight, which causes the projectile to have a constant downward acceleration of approximately 9.81, or g can be taken as 32.2 feet per second square. Thus there is no horizontal acceleration, and the horizontal component of the velocity remains constant throughout the motion of a projectile. As I said, that in horizontal component the acceleration will be 0. So you do not need to take any acceleration or calculate any acceleration along x component or in horizontal component, but we will have acceleration as g, or the gravitational force along the vertical component, or along the vertical projectile motion. For the horizontal motion of projectile, we have equations. Since acceleration is 0, we know that acceleration along x component or in horizontal component, we will have acceleration is equal to 0. So equations for a projectile will be, and these are the equations of motion. V is equal to v naught plus a t. V is the final velocity, v naught is the initial velocity, and a is the constant acceleration, and t is the time time period from point A to time of flight from point A to the point B. So as we know that in the x component we are having acceleration is equal to 0, we will put that acceleration in the first equation. So we will get Vx is equal to v naught of x. Vx is the velocity along x component, and v naught is the v is the final velocity along x component, and v naught is the initial velocity along x component, and this term will be 0, and we are taking x component positive in this direction, so we are having x in this direction positive. So for the second equation, if we will put acceleration 0 in the second equation, we are having x is equal to, x is basically the distance, and this is the final distance is equal to initial distance plus initial distance, or x plus v naught of t plus 1 by 2 acceleration into times square. So we will put 0 in acceleration, and we will get x is equal to x naught plus v naught x. V naught x means that velocity in x direction. Okay, velocity in x direction into t. So we will get this equation from the horizontal component of the projectile motion. Okay, let's see for the third component, we will take or we will put acceleration here 0. So we will also get v square will be vx is equal to v naught into x. So as you can see, the first equation and the third equation are the same, and it tells us that velocity will be the same throughout the x component. So from this horizontal component, we will use this equation for further our problem solving. The first and last equation indicate that the horizontal component of velocity always remains constant during the motion. Okay, now we have the vertical motion of projectile. Since positive y-axis is directed upward, then ay will be negative g. It means that acceleration in y direction will be g, which is negative g, because we will take in y in this direction positive, so it acts on the downward. So for downward direction we will take g as negative g, and g is equals to 9.81 meter per second square. The equations for vertical motions are, that equation will be as we calculated or derived for the horizontal motion, for the horizontal component. Now we will calculate for vertical motion of a projectile. For vertical motion in the upward direction we will take y as positive. So the first equation will be, if we have the first equation is final velocity is equal to initial velocity plus acceleration into t. So if we put acceleration as minus g, so we will get this equation, which is velocity into, or the final velocity in direction of or in component of y is equal to initial velocity of y minus gt. Okay, so we have now the first equation like this for the projectile motion. In projectile motions we will use this equation. Okay, for the second equation we will put acceleration as g or minus g. So we will put or we will get that this equation from the second equation, which is y is equal to y naught plus v naught of y into t minus 1 by 2 g t square. So this is the second equation for the vertical motion of a projectile, and this will be the third equation. The third equation is v square y is equal to v naught square y minus 2g. Okay, 2 is instead of this 2, and acceleration instead of, and this a we will put g and minus g, so it will become minus 2g into y minus y naught. So we get all these three equations from this for the vertical motion of a projectile, and in the first for in the horizontal motion we will get the second equation for our problems. Further we will use that. Okay, now we have examples of projectile motions, and projectile motion refers to a motion of an object projected into the air at an angle. So for that a few examples include which are soccer ball and the baseball, athlete long jumping, and the water fountains. So let's see how it works. Soccer ball is example of projectile motion. As you can see, an athlete is hitting a ball at an angle, and this will follow a specific path or a path in two components, which are x component and the other is y component. So if we want to calculate its velocity, we will have two its velocities in two components. The one will be in x component, the other will be in y component, because it is traveling in both the components. So it will be easy for us if we have its angle, if we have its initial velocity. So from that we can easily find out its range or its final position, or if we have the final position and we want to find out the total flight time, so we can also find that time with the help of these equations we have which we have derived earlier in the previous slides. So here we have a next example of projectile motion, which is a baseball. And in baseball an athlete or a player hit a ball at a certain angle, and it also travels in a car path along the surface of the ground. So if we want to find the range, we will have to know about certain things, which is the angle of projection, the time or the total time of the flight, or the height of the maximum height of this path. So we can easily find out the range, and if we want to find the height, we can also find that height as well. And the velocity as well, we can find the velocity if we have the other values. So we can find these velocity, the time, the range, all these become with the help of these equations. And the third one we have is the athlete long jumping. Same is the case. Athlete is jumping from here. This is his initial position, and this will be its final position. If we know the angle of projection of this athlete and its initial velocities, and so we can find easily its final position. We will know that what will be its final position. So it is all because of the projectile motion and its equations. So now the third we have is the water fountains. In water fountains, as you can see that water is thrown from these positions, and it at the end it goes to our ground at a specific point. So it is because of the projectile motion. Here we will have to know the velocity of this water, the angle of projection of this water. So we can easily design or make fountains or designs like this. We will make a design for a single injector or injector which launch water or throws a water at a certain angle, and its velocity will be known. So we can find out the range will be from this point to this point. So we can find the range and its height of its total height of the its path. So we calculate all these values. We can apply all that properties on all these calculations on the other jets. We will automatically get this pattern, which will be the same as we have designed for the first one. But we should have the same values of the velocity, the same value of angle of projection for the throughout injectors. So we will get this. If we have angle of projection for the first one is 30, and for the second one is 35 or 32 or 33, something like this. So we will not be able to get or to achieve the same pattern or the same path for the second injector as we have designed for the first one. Okay, thank you so much for watching this video. Please subscribe my channel and press the bell icon to get the latest videos.